In this segment, I'll be introducing you to the distinction between training data and testing data in a machine learning context. The problem with machine learning in just using one homogeneous set of data to create and test your machine learning model is that the machine learning model is really good at predicting outcomes that it has already seen. So if you train it on your data set and then use that same data set to test how good the model is, it's going to be pretty good. It's kind of like giving you an exam before the test and then seeing how well you do on the test. So you want to expose the machine learning model to data that it's never seen before, and that will give your best estimate of how that machine learning model will do once it's released into production. Once it's in production, it will definitely be seeing data that it's never seen before, trying to predict, new outcomes. So we handle that in the design set of a machine learning model by taking our data set and dividing it into pieces. Now, as I show on this slide, technically it can be divided into multiple pieces. I show here that there's a training set, a validation set, and a test set. We'll describe those concepts in a little bit more detail in class. For our purposes, in our Excel example, I'm just going to assume we've got a training set in which we create the machine learning model on, and then a test set in which we take that machine learning model and apply it to the test set data and try to predict the test set outcomes. And since the machine learning model has not seen the test set data at all, it's our proxy for how that machine learning model will work once it's released into a production environment and is starting to get real-time observations. Okay, so how are we going to drive these concepts home using our Excel example? Well, this is the model that we had produced previously in trying to predict customer retention. And we had developed in this case, a model that was trained and tested on the same data set, all 3,640 observations in the market site D data. And if you recall, here was the results of the regression that we ran. So that is effectively the trained machine learning model. And then a bit down below, we had created this structure that allows us to take the prediction for each of the observations that was used to train our model, and based on a classification threshold, in this case 0.7, we turned each prediction into a class, 1 being retained, 0 not being retained. And this threshold says, gosh, if the predicted probability from our model is above 0.7 or 70%, we are going to classify this customer as being retained. If it's below that, then we're going to classify this customer as being not retained. And you can see how that is working here. This has got a predicted probability of 0.37, and our class in that case, based on the formula that we've written here, is saying that it's a 0 class or not retained. We then also had this material out here to the side that we added in which we wrote formulas to summarize the confusion matrix. So all of the true positives, false negatives, false positives, and true negatives from our data by comparing our predicted class to the actual class in the data for each observation. And that gave us the confusion matrix, and then we could create these kind of statistical performance measures, accuracy, sensitivity, specificity, and so forth. And then we use an economic model to assess the true value of this machine learning model compared to the status quo. And in the case, the status quo is, we are just going to assume that we keep all of our observations, and then it turns out that we lose all of the ones that are going to be leaving because we took no effort to try to predict who was leaving, and we're wrong in a bunch of those instances because some of our customers do leave us every year. All right, and so we compare the status quo to our predicted model. Our predicted model has these predicted classes, and we do an intervention to try to save them. All right, so this isn't great because in this example where we left off, I am both training the model and testing the model's predicted performance on the same set of 3,640 observations. So how are we going to account for this breakdown of our data from being one homogeneous whole into a train set and a test set? I'm going to go back to our original data, and here I have added this column that I'm calling split. And this is the basis on which I'm going to randomly break apart all of our observations into a test set versus a training set. And I do this by taking advantage of a random number generator in Data Analysis Toolpak. And this allows me to create 3,640 random numbers. I'm going to say uniform random numbers between 0 and 10 million. And it's going to generate that set of numbers, which is already created for us here. So I'm just going to cancel out, get this set of random numbers you can see. And then what I'm going to do is resort the data based on that split, okay, from low to high. And so it has randomly resequenced our observations, which had instead been sorted based on customer ID. Now it's sorted based on this random number that I have created. And I chose 10 million for a reason. It makes it easy for me to do what's called an 80-20 split. Oftentimes, you'll have a particular percentage of the data that you're going to hold aside as your test data, 20%, 10%, 5%, depending on your overall size of your data. Here, we're going to do what's called an 80-20 split, where I'm going to hold aside 20% of my data to be used as the test data, and then I'm going to train my model on 80% of the data. And by putting in a random number between 0 and 10 million, I can find where that approximate 80-20 split is by just going down the random number until I get to, 8 million. And so anything that's got a random number below 8 million is going to be randomly put into my test set or my training set, and anything above is going to be put into my test set. And so once I'm here, I'm going to take advantage of that by running a regression now just on that 80% of the data. And so if I go down into the data here, I've already run the regression on my end, but you can see that the split here is right at row 2917, okay? 2917 rows and above, I've got a random number that's less than 8 million, and 2918 and below, I've got a random number that is greater than 8 million. So I set up my regression so that I am estimating the observations that are 2917, row 2917 and above. And then I'm going to be using the regressors for row 2917 and above. I got my labels on, I've got residuals on, and then I hit OK. And Tableau gives me, or excuse me, Excel gives me this very messy output. I've gone ahead and cleaned it up for you on this tab called Train. And so if we go up here to the top, we can see that there's 2,916 observations here. 2917 was the row, but doesn't count the first row in the data set because that's where the variable names are. So 2,916 observations in our data set gives us the regression results. And I just want to take a second to compare these regression results to the regression results that we get when we use all 3,640 observations. So you just tab back and forth between these two, and you can see that the results are very, very similar. I've got a smaller sample size, right? And some observations aren't included, and my test set isn't included in. So some of the numbers move around a bit, but for interpretive purposes, right, it's like, gosh, what is the impact of pay-go lag on retention? It's around a 3 percentage point increase in retention if you license pay-go lag. We get that in both of these regressions. Okay, so the randomization isn't like pulling a subset of the data in some systematic way. I didn't pull all of the large customers or all of the customers from one particular industry and just run my training set on that. It was random across everybody. Okay, and then what I do here is I have my same setup in my analysis, but I have to be careful, right? Because now my analysis only has 2,916 observations in it. So previously I was doing it for 3,640. So I clean up my my structure here. So I'm only analyzing the set of observations from this set. I make sure that my actual retained value is coming from the reformatted data for the resort of that reformatted data tab. I can't use the old order sequence of retained, or my results are going to be really screwy. Okay, and I can see then if I look at my performance in terms of accuracy, sensitivity, specificity between the full model and my trained model, performance is very, very similar. Okay, and the economic value of machine learning with the full model, it's about 7 million using a cut point of 0.7. The economic value of the machine learning model is about $7 million. In the training set, the economic value is just a little bit less than $7 million. Very close, within $50,000 between these two types of things. Okay, and again, the training set is trained on the training set, and what I'm showing you here is, gosh, if I test on the training set, I get very similar results than if I trained on the whole data set and tested on the whole data set. Now we're going to take it one step further, and I'm going to instead use this model that is created from the training set, and I'm going to use it to predict the observations that were not included in the training set. Anything in row 2918 and below from our reformatted data. And I'm going to do that in, I'm just going to copy training set over to a new worksheet and call it test. So the two models are exactly the same here. If you compare the two of them, exact same regression results. This is the regression results I had on the training set. But I clear out my residual input. Okay, I don't have residual output, that was created by Excel. And in its place on the test set, I'm going to write a formula. And that formula uses a function in Excel called SumProduct. Not super important that you do it this way, but basically what SumProduct makes it easy to do is what we have done manually in class a lot, which is say, hey, this predicted probability is applying this model to this data. And it's starting from 2918 on down, okay? And so I want to take this first observation in my training set, row 2918, and take that profit lag value and multiply it by that coefficient. And then take this PAGO status for this observation, first observation in my testing set, and multiply it by the coefficient on PAGO lag. Right? And I do this over and over again, and writing this formula for SumProduct makes it easy. I write the formula once, and then I copy it down, okay? And then everything else handles for me. I got to make sure that my number of rows, I trim out any extra rows, because in the test set, I only have 724 observations, right? So I trim out any extra rows at the bottom of this thing. And it calculates then for me a confusion matrix, okay, and the performance characteristics. And then this then provides a really good proxy for how would the model perform on new data that it hasn't seen. And the performance is going to be different. And typically, the performance, in my experience, performance has been slightly worse on the test set. But it can be slightly better, and turns out that in this case, if I compare my performance on the training set to my performance on the test set, accuracy gets a little worse in the test set, 84% compared to 85%. But some of the other metrics actually do a bit better. Specificity is a bit better in the test set than it is in the training set. And more importantly, the market value that is estimated is about $7 million in the training set, and it's about $7.2 million in the test set. Sometimes your results will vary dramatically using a holdout test set, and that's a good indication that you've over-specified your model. If you've got a simple, tight, intuitive model, then sometimes you'll get results like we are getting. We don't have a very complex model, and it's basically saying that this model is very flexible. It's not overly tuned to the testing or the training data. And so when you show it new data, it's going to perform about the same. And that's the result we get. Okay, so we'll go over this a bit more in detail in class, and I'll answer any questions, and then we're going to talk about how we can proceed from here with our analysis.